Welcome, everyone. So, in our previous lectures, we've really laid the groundwork, right? We've explored matrices, but mostly in a pretty abstract mathematical sense. Today, we're going to bridge that crucial gap between the theory and the real world. We're going to see how matrix multiplication, which, let's be honest, can seem like just a mechanical exercise, is actually one of the most powerful and, I think, elegant tools for making smart business decisions. We'll see how this one single operation can untangle incredibly complex problems and give us the clarity we need to drive strategy. All right, so here's our roadmap for today. First, we're going to start with a very tangible, real-world problem, a dilemma that managers face every single day. From there, we'll build up our mathematical toolkit. We'll go over the fundamental rules and the step-by-step algorithm for multiplication. Then, once we've got the mechanics down, we'll circle right back to that initial dilemma and solve it with some real precision. And finally, we'll zoom out and see just how essential this tool is across the entire business world. You know, to really appreciate the power of any tool, you first have to grapple with the problem it was designed to solve. So, for the next few minutes, I want you to really put yourself in the shoes of an operations manager at a busy manufacturing company. Just imagine the scale of this challenge for a second. You're not just making one thing. You're overseeing a whole line of products: chairs, desks, cabinets, you name it. And you don't have just one factory. You've got facilities in different cities, maybe even different countries, each with its own production targets. And on top of all that, every single product has its own recipe, a bill of materials calling for specific amounts of wood, steel, labor, machine time. The big question for you as the manager is this: how do you systematically and accurately figure out your total resource needs for the next quarter? Because if you get this wrong, you're either wasting a ton of money on materials you don't need, or you're shutting down production lines. This is not a small question, it's a core operational challenge. Okay, let's simplify this massive problem with the data you see right here. On the left, we've got our production plan. Factory A is set to make 50 chairs and 30 desks. Factory B, well, it has a different target, 40 chairs and 60 desks. Now look at the table on the right. This is our resource recipe for each product. Every chair needs 5 units of wood and 2 hours of labor. And every desk, which was a bit more complex, needs 20 units of wood and 5 hours of labor. So we have these two distinct sets of data that we somehow need to combine. Now, what's so critical to understand here is how fast this simple scenario can scale into complete chaos. I mean, with just 2 factories and 2 products, you could probably figure this out on the back of a napkin with a calculator. But what happens when your company grows? What if you have 15 different products across 7 factories and you're sourcing 50 different raw materials? A manual approach becomes an absolute operational nightmare. It's not just that it's slow, it's that it's dangerously prone to human error. A single misplaced decimal point could lead to millions in wasted inventory, or even worse, production shortages that ruin your relationships with clients. We need a system, a reliable, scalable, error-proof system. So let's build that system. And just like any well-engineered tool, it's built on a very precise set of rules, a solid mathematical foundation. Understanding these rules isn't just about passing the exam. It's about knowing how to use this tool correctly and effectively when the stakes are high in the real business world. Okay, this first rule is the absolute non-negotiable gateway to matrix multiplication. Before you even think about starting a calculation, you have to perform this check. It's called the compatibility condition. The number of columns in your first matrix must be equal to the number of rows in your second matrix. Now, why is that? It's not just some arbitrary rule. It's the mathematical guarantee that the 2 data sets you're trying to combine actually have a logical connection. In our business problem, this rule makes sure that the products column in our production plan lines up perfectly with the products row in our resource list. Without this check, the calculation would be, well, mathematically impossible and conceptually meaningless. This slide here really illustrates that rule perfectly in symbolic terms. Let's say we have matrix A with dimensions m by n. That's m rows and n columns. And we have matrix B with dimensions n by p. To see if we can multiply A times B, we look at the 2 inner dimensions, the n from A and the n from B. See how they match? That means the multiplication is valid. Think of it like a lock and a key. They have to fit. Now look at the invalid case on the right. If matrix B had dimensions k by p, and k is not the same as n, then the inner dimensions don't match. The operation is undefined. It's a mathematical dead end. And here's the second part of that rule, which is just as important. Once you've confirmed that you can multiply, the size and shape of your answer matrix are already set. You just take the outer dimensions of your original matrices, the m rows from the first matrix and the p columns from the second.
So your resulting matrix will have dimensions m by p. This is so important because the dimensions of your answer tell you exactly what kind of information it holds. It reveals the structure of the business intelligence you've just created.
All right, so we've established the critical prerequisite. We know if we can multiply. Now, let's get into the mechanics of how to actually do the calculation. We're going to break down the precise algorithm, a process that, I promise, with a little practice, will become second nature. The entire process of matrix multiplication, believe it or not, boils down to one single repeated operation, what we call the row-on-column method. To find any given number in your answer matrix, you systematically take a row from the first matrix and a column from the second. Then, as you see on the slide, you multiply the corresponding elements together. First element of the row times the first element of the column, second times second, and so on, all the way down. Finally, you just add up all of those products, and that sum becomes one singular element in your new answer matrix. Every single number in your final result is calculated exactly this way.
Let's make this really concrete with the example on the slide. We've got two simple 2x2 matrices, A and B. First things first, we do our compatibility check. Matrix A is 2x2, matrix B is 2x2. The inner dimensions are both 2, so they match. We're good to go. And we also know from our second rule that our answer, the resulting matrix, is going to have the outer dimensions. It's also going to be a 2x2 matrix. Okay, let's actually run the row-on-column algorithm for that very first element. To get the entry in row 1, column 1 of our answer, we take row 1 from matrix A, that's 1, 2, and we take column 1 from matrix B, which is 5, 7. Now we multiply the corresponding elements. 1 times 5 is 5, then 2 times 7 is 14, and finally we sum those products. 5 plus 14 gives us 19, and that, 19, is the very first element of our resulting matrix. And now we just repeat that exact same process for every other position in the answer matrix. So to get the top right element, we use row 1 of A and column 2 of B. That's 1 times 6 plus 2 times 8, which gives us 22. To get the bottom left element, we use row 2 of A and column 1 of B. So 3 times 5 plus 4 times 7, which is 43. After we do that one last time for the final position, we arrive at our final product matrix just like you see on the screen. 19, 22, 43, 50. Okay, now for the real payoff. We've gone through the rules, we've practiced the algorithm. It is time to go back to our factory manager and give them a definitive solution to their problem. This is that moment where the abstract math we've been doing delivers real, tangible business value. The first, and honestly the most crucial step in any business application of matrices, is structuring your data correctly. So we'll take our production plan and organize it into what we'll call the production matrix P. In this matrix, the rows will represent our two factories, A and B, and the columns will represent our two products, chairs and desks. Okay, next up is the resource matrix, R. Now, this is the key part. For the multiplication to be valid and to actually mean something, the rows of R must correspond to the columns of P. So the rows of R will represent chairs and desks, and the columns will represent the resources, wood and labor. Do you see how the inner dimensions, products in matrix P and products in matrix R, now logically line up? Our setup is valid. So now we perform the multiplication, production matrix P times resource matrix R. Let's just walk through that top left element again, which represents the total wood needed for factory A. We take row 1 of P, 5030, and multiply it by column 1 of R, 520. The calculation is 50 chairs times 5 wood units for each chair, plus 30 desks times 20 wood units for each desk. That gives us 250 plus 600 for a grand total of 850 units of wood. Now, when we complete the whole multiplication, just look at that beautiful result. We don't have a mess of scattered numbers. We have a clean, perfectly organized report. The rows tell us the factory, the columns tell us the total resources needed. As a manager, you have instant actionable intelligence. You know with absolute certainty that you need to order 1,400 units of wood for factory B and schedule 380 hours of labor. The dilemma is solved. I have to emphasize this next point because it is the most critical conceptual mistake that students make. In all the arithmetic you've known your entire life, order doesn't matter, right? 5 times 4 is the same as 4 times 5. We call that the commutative property. Well, in the world of matrices, that property does not hold. A times B is almost never equal to B times A. The order of multiplication fundamentally changes the question you are asking. In our problem, P times R correctly asked, what are the total resources needed for each factory? If we had tried to calculate R times P, what would that even mean? We'd be multiplying a resources per product matrix by a products per factory matrix. The result would be some nonsensical table of resource factories? The order you choose is your model of the business problem. And if you get it wrong, your conclusions will be dangerously flawed.
Now, it is so important that you don't just view this as some clever trick for solving production problems in a textbook. This elegant method for organizing and combining data is actually a cornerstone of modern quantitative analysis in almost every field of business. Let's take a look beyond the factory floor. Understanding this concept is crucial because it's the mathematical engine that drives so many of the complex systems you're going to encounter in your careers. In economics, they use massive input-output matrices to model all the intricate dependencies within an entire national economy. In finance, portfolio managers use something called covariance matrices to quantify and manage risk across hundreds of different assets. In supply chain management, giants like Amazon and FedEx use matrix operations to solve unbelievably complex routing problems, optimizing their global delivery networks in real time. Even in marketing, your user data is organized into vast matrices to generate recommendations. That whole customers who bought this also bought feature, that's powered by this exact math. It is everywhere. So, to wrap up our lecture today, I want to leave you with a question to carry forward into your professional lives. Don't think of this as just a chapter in a textbook. Think of it as a fundamental analytical tool in your toolkit. Whether you go into finance, marketing, operations, it doesn't matter. You will constantly be faced with large, interconnected sets of data. And your success will often depend on your ability to structure that data, ask the right questions, and pull clear, actionable insights out of all that noise. Matrix multiplication is one of the most powerful methods ever devised for doing exactly that. So I ask you to consider, what complex questions in your chosen industry are just waiting for the structure and clarity that a matrix can provide?